Okay, guys, Chapter 2, Parts of a Computer System. We're going to kind of go through everything. The first one is something I hope that you will recall from 1430, the basic components of a computer. And let's first start with probably the thing that nearly everybody will recognize, and that is the CPU, Central Processing Unit. Central Processing Unit has a lot of components, several of them though, in particular we're going to be interested and we'll talk more about them as we go. One is the control unit, the arithmetic logic unit, and also something that's going to come into play quite a bit with low-level programming is a series of temporary high-speed storage locations that are part of the CPU called registers. So that's the first piece, and actually I guess we could consider it multiple pieces. The next piece I want to talk about is probably the primary connection between CPU is CPU and memory. So let's draw memory. We're going to draw it just for convenience as a table, although remember, memory is not a table. It is linear. In other words, I access it in several different ways. Probably the easiest one just to think about is I start at the beginning. This piece of memory that has its own unique address, start there, and then I march through the rest of them until I find the piece of memory that I'm looking for. So, but do remember that it is linear. It's not a table. Memory, also known as random access memory. Okay? Interesting thing. It's called memory. Random access memory only holds data when power is supplied to the machine. At other times, for example, if your kid's sister kicks the cord out, everything that was in random access memory is gone. All right, how do you get things into a computer? Well, we have input devices. So, several different input devices. Probably standard in, which is a term you'll use quite frequently, is the keyboard. So we'll call the keyboard standard input. Let's say keyboard. Let me show you. Oops, that's bad spelling. That's okay. Standard in is what you'll see that called a lot of times. Other input devices would be the mouse, maybe a microphone. Oh, you guys, there's lots of different input devices. How about when I type something? Let's say I'm typing a letter. How can I tell that what I'm typing is actually what's getting recorded? Well, I have a series of output devices. And again, just as there is with input, there is a standard out that is the monitor. STD out. You also have speakers, maybe printer. Oh my, there's a lot of them. So anyway, the list goes on, but we have more to talk about. I also have, so we said that random access memory is temporary memory because it only exists when power is supplied. So how do I handle situations where I need to store things for longer term? Well, I do have something else. Oh, and you know what? I forgot to draw communication between these two. All right, and I'm going to show this coming from the CPU, but realize that most of it goes CPU and memory to something called auxiliary storage. or permanent storage. Well, at least more permanent than RAM. This would be hard drives, flash drives, a DVD read-write, things like that. So these are the basic components of a computer. What we're going to be emphasizing for most of this course is really the interaction between the CPU and memory. Okay, what else have we got? Structure of a computer. Let me talk a little bit about the generic memory map, because what happens when you turn on your computer, power is supplied to the motherboard and then to all the components. Probably one of the first things that happens, though, is that power supplied to memory, and a memory check is done. And then the kernel of the operating system is loaded, along with system routines and read-only memory routines, input-output device drivers, things like that. So, and I call this generic. Let me just point this out and make sure you realize this is generic. This is not the case for everything. So, things we mentioned: system routines, user programs, user data, and then so on. And we get down to maybe my read-only memory routines here, and then followed by I/O device drivers, where for all of this stuff, low memory is where the system routines are, and going down to high memory, where we have input-output devices, read-only memory routines, etc. So it kind of just gives you a basic idea of where things are stored. Speaking of memory, how do we get to different chunks of memory? First, let me point out one thing that's kind of important. Most systems address a specific size of memory at a time. So for us, most of the stuff we're going to be talking about is byte addressable, meaning each byte in memory has its own each memory or each byte has its own memory address. So first of all, let's talk about flat memory model, because flat memory model is, let me just draw you a picture. Flat memory model, let's say we start memory here, and at some point we're going to have a whole bunch of memory that we don't see. Remember, we said it is linear. Okay, there is byte 0. Oops, byte 0. I can, in a flat memory model, this will go all the way from 0 to n-1, where n is the total number of bytes that I have that are addressable. So that's flat memory. The programs actually encode 32-bit addresses to logically reference locations, in this case, in a single memory space, where both data and instructions are stored. So in segmented memory, what we do is memory is viewed as a collection of segments. Let me change colors. A collection of segments. Maybe that's a segment, that's a segment, that's part of a segment. Each of these segments is, depending on the total amount of memory that you have, somewhere along the line of 65 kilobytes long, and it starts on an address that's a multiple of 16. This makes it just a little bit easier, again, to jump from segment to segment. Each memory address or reference depends on its segment number. So this would be segment 0, segment 1, and so on. And then within that, let's go over here to this one. Within that memory address, I might jump from byte to byte inside. So I've got an offset from the start of the segment. How many bytes away do I need to go? So in segment offset, or segmented memory, you will see addresses not as 32-bit addresses, but you'll see them in segment offset pairs. So back in the old days, you might have seen something like this. So for this segment and maybe this byte, it would have been, let's just give an example. Okay, where this was the segment and that was the offset, or how many bytes away from the beginning of the segment is the byte I need to get to. So those are the two different models that we're primarily going to be focused on in this course. So whereas the machine will use segmented memory and paging, I'll talk about it in a minute, we're going to be using flat memory. So we're going to let the machine handle the conversion between the two. Okay, paging. Yes, good, that's next. Paging, addresses that are generated are not necessarily the physical addresses in a paging mechanism. The mechanism is used to map the program's addresses into a physical address. So in operating systems, paging is a memory management scheme where I can store and retrieve data from secondary storage, like our hard drive, for use in main memory. So when I start to run out of memory, I can move things from random access memory into auxiliary storage or hard drive. So paging is an important part of virtual memory implementation in most operating systems. And it allows, again, basic usage of the disk storage for data that's not fitting into the physical RAM or random access memory. So let me just say, for the most part, it's awesome, but it's going to be transparent to us. The only time it's not transparent is when virtual memory doesn't work. And then you'll notice it. Okay. The instruction execution cycle. Let's do as much of this as we possibly can. Let me just say, let's draw some things first. So I want to draw CPU, and I've got control unit, I've got AL unit, and then I've got some registers. And let's say one of these registers is called EIP. We'll talk a little bit more about all the registers in a minute, but for the purpose of this is also called the instruction pointer. This holds the address of the next instruction to be executed. So let's show the connection between this and RAM, or random access memory. And let's say we want to walk through a particular example where we are, here's our instruction that we're going to use for our example. Okay, let me just tell you quickly, this is the opcode or mnemonic, so we're adding some things. The next two things are the operands. So this is a direct memory address. It is our destination. This is an immediate value. It is the source. So usually I go source to destination. It's important to note because when I'm, for example, in this example, adding something, the result is going to be stored in the destination. Okay? So that's what we're doing. First thing that happens is this instruction is going to be stored in random access memory. So let's go over here and see if we can draw it out where we can see it a little bit better. Okay, so let's say in here I've got the bytes that hold the information that tells me that I am adding 5 to some. Okay? What's going to happen is, oh, and before I tell you what's going to happen next, I need to actually show you how these are connected. So, I've got a couple of buses. This is the address bus. This is the data bus. Data bus goes both ways. I've got other buses, but we'll start with that. So, what's going to happen in this example is I will find out what is in EIP and take that address, put it on the address bus, go out to that place in memory, read the next 2 bytes, bring those across the data bus to the control unit. Okay? Control unit is going to translate and say, oh, okay, I'm adding a couple of things. From both of these bytes, I know that I'm adding an immediate value to a piece of data or another value that's stored in memory. So I'm going to have to, by the way, now that I've come back across the data bus, EIP will have incremented by 2. So next time, what I need to do is, after I read these 2 bytes, I know I'm adding an immediate value to a place in memory, but I don't know what the immediate value is, nor do I know where the place in memory is located. So I have to take what is in EIP, put it back on the address bus, go back. Now I'm going to go here because EIP got incremented after the last time. I do this for a couple of reads and get the destination. I bring that back to the control unit. I put that address back on the address bus and go somewhere else in memory to pull whatever is in sum. Let's say what's in sum is the value 12, for example. I pull that and I bring it across the data bus into the control unit. And then actually, it's going to be stored temporarily, but at this point, I'm going to do one more read across the address bus, +2, +2, +2, go back across here where I'm going to have another couple of reads to read the immediate value. Immediate value is there. Location of sum. I know this is detailed. We will spend a lot of time this semester on this. This, guys, the instruction execution cycle is at the heart of everything that we do. So it's an important thing. It's not a bad idea to spend some time on it. Once I've gone out, read that immediate value, put it on the data bus, then I now have the value stored in memory. I have my immediate value. In the AL unit, I will add them together. So here, I have 5 plus 12. Since, in this example, sum is our destination, when I am done in the AL unit, I will put the address of sum on the address bus and go back out to that place in memory. And I will put my result on the data bus and store it. Okay? Every time I do this, my instruction pointer gets incremented by 1. Wow, what a nasty mess that is. But in class, I'm going to show you an applet that kind of steps through this a little bit cleaner, because it's not me drawing. Okay, so how's all this stuff stored in a computer in memory? We kind of alluded to this. Right here, I've got my mnemonic. I know I'm adding. Let's say, and I'm going to show this in hex. let's say the mnemonic for adding an immediate value to a place in memory is 83 hex. Now I need to know a little bit about my operands, so and again, when we get a little bit later in the semester, I'll show you how exactly this information is encoded. I'm going to need another byte that has the information for how I'm addressing the information in each of these operands. So we said that's an immediate value, that is a direct memory address. That information is going to, how I'm addressing is going to be stored in the next byte. And let's just say it looks like that in hex. The next thing that's going to be stored is the address of sum. Well, let's say sum is at 00162820. And then finally, I've got to have that immediate value stored. So here I will say this. Okay, so this is my opcode. This tells me information about how I'm addressing my operands. This is the address or displacement for sum, and then this was my immediate value. Okay, if I look at it in memory, that's what it looks like. If I look at it as a machine, it looks like all of that in, oh my, okay, let's see if we can do this, in binary. So, yuck. Oh, we'll see how long we can put up with this. Two, where am I? There I am. Oops, that's a 0, 1, 0. And then finally 0, 0, 0, 0. Dot, 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 0, 1, 0, 1. And that, this last part was our immediate value, 5. This part was the displacement. There's my opcode. That's the byte that tells me about my data, how I'm addressing my operands. Okay, so computer system diagram. You know what? We will do, remind me when we get in class, let's go back and do some examples so that we kind of walk through this and talk a little bit about it. Alright, and this is a little bit different drawing. I see that I still have a CPU here. Whoops. I still have my CPU. I've got memory. One thing I want to point out, this is an old diagram, so it's, you know, it's not as current as it would be. I would tell you that for most systems, cache is now part of the CPU. So when we say cache, if you've ever looked at technical specifications, like this would be things that would be referenced by something like L2 or L3 cache. Cache is similar to registers in that it is very high speed, also temporary, because it allows us to store more of what we're pulling from memory and keep it in the CPU. That makes the system faster. Now, one thing I want you to notice, as we are going through our instruction operation cycle, remember that we are always going between the CPU. Let's say I go to the CPU, I go out to memory, get a piece of information, maybe it's the next opcode, bring it back, go across and get something in memory again, bring it back, maybe add something in the AL unit, and then take it back. That's for one instruction. So the next instruction, guess what it's going to do? Well, it's going to take the next address, go out, pull that address, bring it back, get the rest of the instruction, bring it back, get an immediate value, bring it back, do the math, and then store it. So I only tell you that because I want you guys to realize that the bottleneck for, let's the bottleneck for everything, let's redraw that, is going to be the system bus. Because everything that we do has to travel across that system bus. That system bus has a fixed size. So when you say you've got a 32-bit bus or a 64-bit bus, each one of those, 32 in our case, would tell us that I've got 32 lanes of binary traffic. So I can put up to 2 to the 32 values on that bus at a time. So I can only get to a certain part of what's in memory, and I can only get to it with that much space. So everything we're doing is going from the CPU to memory and back, so I'm always traveling across the system bus. That's the bottleneck. Alright guys, let's finish the rest of this.